Okay, so 7 starts off with a fairly straightforward proof by induction, as long as you can multiply matrices. So make sure you get all your statements right. So first of all, we're going to start with n equals 1. So if n equals 1, the left hand side is 4 minus 1, 9 minus 2 to the power of 1. And the right hand side is going to be 3 plus 1, negative 1, 9 times 1, 1 minus 3, which is going to be 4, negative 1, 9, negative 2, therefore true for n equals 1. Okay, so then we're going to assume for n equals k, so we assume that 4 minus 1, 9, negative 2 to the power of k is 3k plus 1. Okay, now it's always worth having a little aside, thinking where am I trying to get to in my proof. So I need 3 times k plus 1 plus 1, 9 times k plus 1, negative k plus 1, 1 minus 3, k plus 1. Okay, so then we're going to go for n equals k plus 1. Okay, so with matrices, we split that up into the matrix to the power of k times the matrix to the power of 1, so i.e. itself. So then we're actually going to do some matrix multiplication. Well, we're going to use, first of all, we're going to use our assumption for that one. Okay. And then we're going to do some matrix multiplication. So remembering our matrix multiplication goes first row, first column, second row times first column, in the second row, first column, etc. So this top one's going to be 4 times 3k plus 1 plus 9 times negative k. So this one is second row, first column, so it's going to be 4 times 9k minus 9 times 1 minus 3k. First row, second column. And second row, second column. And then we're going to simplify all that. k plus 1 minus 9k, so it's going to be 3k plus 12k plus 4, take away 9k, it's going to be 3k plus 4. Here we get negative 3k, negative 1 plus 2k. So here I'm going to get 36k, take away 9. If I multiply something wrong there. Oh yeah, then plus. I think something might have gone wrong with my signs there. We'll have a look at that in a sec. The last one's going to be negative 9k, take away 2k plus 6k, so it's going to be negative 3k, take away 2. Okay, so the error here was actually, I just put a negative there, and that should have been a positive, so that becomes 36k plus 9, take away 27k, which gives us 9k plus 9. If we have a look at what we're trying to get to, can I factorize this to be what we're trying to get to in terms of k? So yes, this is 3 times k plus 1 plus 1. This is negative k plus 1. This is 9 times k plus 1. And this can be rewritten as 1 take away 3 lots of k plus 1. So it is true for n equals k plus 1. Okay, now the conclusion for proof by induction is quite long, so I've just copied it from the mark scheme. The important thing is that you get all the things that are underlined in your conclusion. Okay, so the second part then went on to get you to look at a response, and they want you to prove a statement. So the first bit is we're using a counterexample to show that a statement is not true. So all you got to do is come up with something that proves it's not true. So we're looking at this statement here. Let's see. So if n is 1, it's true. But if n is 2, then 2 squared is 4, and 2 to the power of n is the same, is also 4. So n squared is not less than 2 to the n, it's equal to 2 to the n. So we've proved it's not true. So then they're telling us the only mathematical error is in line 4, and conveniently they point that out. Identify the error. Okay, so let's have a look at this. So what error have they made? So they've gone through, they've said k plus 1 squared is equal to this. They said that's going to be equal to the less than k squared plus k, since 2k plus 1 is less than k squared. So this is their assumption as to why they can replace 2k plus 1 with k squared. The problem is that's not always true. Because, for example, so let's have 2k plus 1 is not always less than k squared. Okay. Sorry, say that is not always true, and then all you've got to do is find an example where it doesn't work. So you, well, first of all, you're going to have to work out for yourself that it's not always true. Well, she's also talking about k coming from the set of integers. But for example, if k equals 1, so we're doing a counter example again, then 2 plus 1 is not less than 1 squared. So it's not true. Right, so that's then a bit of a problem. So they want us to find which positives integers the statement is true and explain our reasoning. Alright, so we're going back to the original statement, which was this. Okay, so here is our original statement. So we want to know when is this true? Well, there's several things we can look at here. So here's the student answer, and they said the only error was this one, and we've now identified the error. So we can think about, so when is 2k plus 1 less than k squared? Well, we know it didn't work for 1, doesn't work for 2, but once we get to 3, it does work. So that is true for k greater than 2. Okay, so that means the induction step is going to work for n greater than 2. Okay, so this bit is going to be okay as long as k is greater than 2. So that's fine, but what else can we say? Well, if we look back at our base case, when we started this off, we considered this statement. Now she said it's true for n equals 1, and that's okay, but in part A, we showed that it's not true for n equals 2. So we can't start with the base case of n equals 1. We can't start with n equals 2 because we showed it wasn't true. Can we start with n equals 3? Well, 9 is less than 2 cubed. 2 cubed is 8. No, so we can't state with 3. Is it going to be true for n equals 4? 16 less than 2 to the 4. No, they're the same, so it's not true for that either. So they're all counterexamples we could have used in part 8. But once we get to n equals 5, the base case is now 25 less than 2 to the 5. That is true. So now the base case is going to hold. For n equals 5, the induction will hold. Because we said that's true for k is greater than 2. You could check yourself as well and make sure that n equals 6 works if you can just think about it in your head. And therefore, the induction works for n greater than or equal to 5. Now there's quite a lot of words there, so what I've just done here is copy the mark scheme so you can see what they wanted you to say. If you're not sure about this, also when this statement is true, other than just thinking about numerically, you can also think about when that quadratic is going to be greater than 0, and that can help you think about it as well if you rearrange it to make a quadratic. But that's the wording from the exam, just a lot of thinking about numbers.